Welcome to the second part of the solutions to the lecture problems for Chapter 7. We begin where we left off, which is question 5. Here we're told that a small particle of mass m is pulled to the top of a frictionless half cylinder of radius r by a cord that passes over the top of the cylinder. We are to assume that the particle moves at constant speed. Now that is very important, and note that it says here no tangential acceleration, which means that A tangential will be equal to 0, so the speed portion will not change. However, since this particle is undergoing motion along the circle, the semicircle, at constant speed, there will be a centripetal acceleration, which is equal to v squared over r. So no tangential acceleration means constant speed, but the fact that the motion is occurring so that the direction is changing means that there is a centripetal acceleration. We are to show that the pulling force is equal to F equals mg cosine of Q. So let's see if we can, we're losing our pencil here. We are to show that F, the magnitude of, is equal to mg cosine of theta, because this Q is interpreted as a theta by this notebook system. All right, and then we're asked to determine through direct integration what the work is to move the particle at constant speed from the bottom to the top of the cylinder, not to the end of the cylinder, the half cylinder, but to the top. And so here, let's just make a note that the angle will be pi over 2, and here the angle would be 0. Okay, well, let's begin with the first part of the problem. We know that because there is no tangential acceleration, there will be no force which is tangent to the motion. Now, let's see if we can draw a free body diagram of this bead as it is shown to us at this point. Here, you can see that there is a force acting, and here the force appears to be tangent. However, keep in mind, no net tangential force implies that this has to be balanced at least by a component which is in the opposite direction. In fact, because we have the force of gravity acting on our bead, mg, this component will be mg cosine of theta, the angle theta that has been traced out by the position of this bead, and this angle and this component here is mg sine of theta. So while there is no net tangential force, we note that we do have a force that is tangent, that is given to us, F minus mg cosine theta equals 0. And quite simply, we have solved the first part of the problem, which was to show that F must equal mg cosine theta if there is to be no tangential acceleration of this bead. Now, in the second part, we're asked to, by direct calculation, determine the amount of work which is done by this force as the bead is displaced a distance which is equal from the bottom of the arc to the top of the arc of the semicircle. So we have our force, which is tangent. We have ds, which is given as r d theta, okay? And that is, so let's make a little note here. ds is also tangent to the path. F is given as tangent to the path. And when we take a dot product, because they are both parallel to each other, we get mg cosine theta times r d theta. Well, let's see. We have some constant quantities here. Mg r, integral of cosine theta d theta from 0 to what we said earlier, pi over 2. Well, the integral of cosine theta d theta is sine theta d theta. So sine theta from 0 to pi over 2, of course, gives us 1. And so the solution becomes mgr. So for some given value of m, g 9.8, and r, the radius of the semicircle, we can determine the amount of work which is done by this force. Okay, next problem, question number 6. To measure the spring constant K, a spring is hung vertically and a mass is attached to the lower end. Under the action of the load, which is, by the way, the mass, it's known as the load, the spring stretches a distance d from its equilibrium position. We're told initially that the mass of the load is given to us as 0.55 kilograms, and that the displacement downward that this mass undergoes is, and we're going to indicate downward with a negative sign, 0.002 meters. And of course, let's just be sure we put a little J hat there because we're pointing downward. We look at the free body diagram that's presented here. Fs equals minus Ky. Okay, and so using Newton's second law, see, chapter 5 comes back to haunt us. The net force in the y direction equals 0 once the equilibrium is reached. So we're told then we've got minus Ky upward, minus mg downward. So minus Ky equals mg, and we're solving for k, so k equals mg divided by minus y, but of course y itself is negative, so k will be given as a positive value, 2,695 newtons per meter. In the second part of the problem, we're told if instead for that same spring with spring constant which has just been determined in part A, if instead we use a 1.5 kilogram load or mass, oops, we got blue now, determine what the value of y would be. Well, here we're going to just take a reversal and solve for minus y as mg divided by k. And what we get is that minus y is equal to 5.45 e to the minus 3 meters, or in other words, y, the displacement that this mass would undergo, would be negative 5.45 e to the minus 3 meters. And again, the negative sign to remind us that it is a displacement which is downward. Okay, now the last part of this problem asks us to determine the amount of work. So this is part C, this was part B. The amount of work which is done by the spring force when the mass undergoes a displacement of 0.02 meters. Okay, so work is equal to the integral, and here we must be very careful that we use the integral form because F sub s is a force that is variable with displacement. Okay, so we have to keep that in mind, and our displacement will be from 0 to minus 0.02 meters. Okay, we have to keep in mind, and our dr only has a component which is dy j hat. F sub s only has a j hat component, so when we take the dot product, we end up with minus ky dy. This would just be multiplication, by the way, because we've already taken the dot product. They're both in the same direction. So solving for the integral, minus k y dy becomes y squared over 2, from 0 to minus 0.02 meters. And when we plug in all our numbers, we get a value, we have a minus let's see, what have we got here? We're going from 0 to minus 0.02. We get a result which is minus 0.539 joules, which is the amount of work that is done by the spring force when this spring is displaced from 0 to this position 0.02 meters below. Okay, so let's look at next problem. Here, question 7 gives us a graph and tells us that there is a 4 kilogram mass which is subject to a net force, and this net force only has a component in the x direction, so F as a force is only given as Fx, some value Fx I hat. But Fx varies as the object moves through position. You can see here Fx grows from 0 to 3 newtons. Then over this time period of 5 seconds to 10 seconds, let's write 5, we already have our 10 here. We see that Fx is constant, but over the next 5 seconds, when we go from 10 to 15, sorry, not seconds, meters, I should say. This is meters at the horizontal. You can see that the value of Fx drops down to 0. So we do have a variable force, which means that we should, to determine the work, as we're asked to, should use integration. However, please remember that integration is the equivalent of finding the area under the graph that's bounded by the horizontal axis. So what we can effectively do is to split 3 areas here. The first area is 1/2 5 meters times 3 newtons, which gives us 7.5 joules. The second area is 5 meters times 3 newtons, which gives us 15 joules of work. And the last area is 1/2 5 meters times 3 newtons again, the height of the triangle. So effectively we're finding the area of 2 triangles, 1 rectangle, and we're summing the value of these areas to obtain the net amount of work, which you can see adds up to 30 joules. So the total work which is done by this force over the displacement of 15 newtons altogether, 15 meters altogether, is 30 joules. Now, the next part of the problem asks us to determine the kinetic energy and the speed of the mass when it's located at those three positions. Let's see. Well, when it arrives at x equals 5 meters, we know from our determination earlier that work was equal to 7.5 joules. However, by the work kinetic energy theorem, we also know that the final kinetic energy minus the initial kinetic energy is equal to the amount of work which is done. Now, since the particle starts from rest, the initial kinetic energy is 0, and so the final kinetic energy is simply 7.5 joules. Once we obtain the final kinetic energy, it's very straightforward to obtain the final velocity, since it will equal the final kinetic energy multiplied by 2. Here we're solving for V final. We have a square here that we forgot. Divided by the mass of the particle, which is 4 kilograms. Square root. That gives us a value of 1.94 meters per second. So when the particle reaches the position x equals 5 meters, it has 7.5 joules of kinetic energy, and its speed is 1.94 meters per second. How about when it arrives at 10 meters? Well, here the work will be the sum of the two areas, not just one here, because now we have 7.5 plus 15, which gives us 22.5 joules. Here again, no initial kinetic energy, so K final equals 22.5 joules. And we proceed to solve for V final. 2 times 22.5 joules divided by 4 kilograms. That gives us, that's 4 kilograms. That gives us a speed of 3.35 meters per second. And so that is the final speed of the particle when it reaches x equals 10 meters. Lastly, when the particle reaches x equals 15 meters, we know the work is equal to 30 joules, the total amount of work. K final equals 30 joules, again, because K initial is equal to 0. V final, again, same thing. We plug in our numbers and we get a V final. I'll just write the final result, 3.87 meters per second. And so effectively, we have solved for this problem, the work, the kinetic energy, and the speed of the particle without ever having to use integration. However, that will not be true for the next problem. This problem here tells us that there is a force 2y I hat plus x squared j hat that acts on a particle as the particle moves from x equals 0 to x equals 5 meter and y equals 0 to y equals 5 meters. We are asked to determine the amount of work done by this force along two different paths, and when we compare the amount of work, we have to determine if that force is conservative, and the answer will quite simply be if the work done by path OBC equals the work done when the particle takes the path OAC, then F is conservative, and in fact, a further check would be to check whether this equals the work that is done as the particle goes from O to C directly. That would be 3 checks, but any 2 given paths, if the number is equal, then we know the force must be conservative. If we want a further check confirmation, we can determine the work done by a 3rd path, and then a 4th if we want it to be even that more certain. that our force is conservative. However, if the work does not equal, okay, for either of these, then F is not conservative. And so our task is to determine whether or not the work equals between one path and the next. All right, let's begin by examining the work done from O to B. Now, the first thing we must do is to write dr as a vector, which is dy j hat. Dx is equal to 0, and so there will be no variation in the x. Okay, let's go ahead and work through the integral. The work is equal to 2y I hat plus, now the value of y over this remains 0, while x goes from 0 to 5, and because y is equal to 0, oh, sorry, here from O to B, sorry, it is x which is equal to 0, and y goes from 0 to 5. Okay, so it's my mistake here. There is a variation in y, as I just mentioned, but not in x. In fact, the value of x is equal to 0. So here, 2y I hat plus 0j hat dotted with dy j hat gives us 2 times y dy from 0 to 5, and this integral becomes 2y squared over 2 from 0 to 5, and so this tells us that the work is equal to 25 joules. The 2's cancel. Okay, that's from O to B. From B to C, which is the next leg of the path, dr is equal to dx I hat. There is no variation in y. In fact, y equals 0. Sorry, y equals 5. X goes from 0 to 5. Okay, so let's see. So the work done is equal to 2 times y is equal to 5, 2 times 5 I hat plus x squared j hat, and that gets dotted with dx, oops, get our pencil back, dx I hat. Okay, now what's the problem here? Well, let's see. What have we got? Well, we have no variation in y, so we have dx I hat here, so our j hat term is not going to yield us any value, so we've got 10 times dx as x goes from 0 to 5, and this gives us, let's make sure we did this right, 2y plus x squared. Okay, this gives us a value of, in fact, the first one, actually this right here is incorrect. As I go back and look, 2y I hat plus 0j hat dotted with j hat, this term dotted with I hat dotted with j hat is 0, so actually we get nothing from the first term, and 0j hat dotted with dyj hat is 0. So actually this is incorrect. I apologize. I knew there was something funny. I'm getting my I hats and j hats mixed up. The first integral gives us 0 amount of work. It's this integral which is actually going to supply the work. 10x from 0 to 5 gives us 50 joules of work. So I apologize. Please note the error that I made. Go back and have a look to make sure that you understand why this first integral is 0. All right, now let's check the next path. The next path is from O to A. Here, dr is equal to dx I hat, dy equals 0, so there's no variation in y, and y has a value equal to 0, x goes from 0 to 5. Okay, the first integral for the amount of work is equal to 2 times y, which is equal to 0 I hat, well, that will be 0, plus x squared j hat, x squared j hat, and the whole thing dotted with dx I hat. Here again, look, I hat has a value of 0, and the j hat component, even though it's got an x term, j hat dot I hat is 0. So in fact, this integral, like the first one in the part that we just did, is also equal to 0, the one from O to B. Okay, the next one here is A to C, and here dr equals dy j hat, dx equals 0, and here we have x equals 5, y varies from 0 to 5, so the work is equal to 2y I hat plus 5 squared j hat. All of this gets dotted with dy j hat. And so here I hat dot j hat is 0, so we get nothing from the first term. So our integral becomes 25 dy as y goes from 0 to 5, and that becomes 25y from 0 to 5, giving us 125 joules of work. And when you compare the 75 joules of work that we had earlier with the 125, or rather, I should say the 50 joules of work that we had earlier, compared with the 125, you can see that there is a big difference. The difference being, of course, what I just said, 75 joules. Therefore, this force we can say is non-conservative. Okay? We could check the third path, but if two paths give different values of F, it is not necessary to check the third. Well, this concludes the second part of the problem solving session for Chapter 7. Until next